This is epsilon Fermi, and new variables will be minus epsilon Fermi. But I extend it to minus. You will see that the integral is convergent. Very good. So for I can leave it if you want. But in isotropic case, this is so I will put here. So my integral will pass to this. And density of states I will take at the Fermi level, constant. And so I will pass this integral will be integral d omega for pi mu of epsilon Fermi integral dc, and what in denominator? My green functions. Because if I pass now the calculation of p, so p will be p omega nu will be t sum over epsilon n. Now integral d omega for pi integral at minus infinity mu at the Fermi level d psi e epsilon n plus omega nu minus psi of p plus q multiplied 1 over minus e epsilon minus psi of p. That's all. But yes, please.
This trick when we pulled out density of state at Fermi energy.
Yes.
I think at this point we assumed that density of state is somehow peaked around omega d pi, right?
Not omega around epsilon Fermi.
Around Fermi energy, but on some short range.
Exactly.
So
we are interested only in this. We know that other electrons do not participate in because we remember that our G is a result of Coulomb repulsion plus electron phonon interaction. Electron phonon interaction works only in the limits of omega d pi. So in our model, out of omega d pi, no sense to integrate because the interaction is zero. Okay, so you still follow me or already lost? Okay, so how to calculate integral from minus infinity d psi e epsilon n plus mu minus psi. Now I will immediately expand psi. So I will say that q is small. So I will say that psi of p minus d psi over dp p minus d epsilon n minus psi.
I have a question.
Yes, please.
If we are only integrating in basically a ball skin like orange skin like
yes
volume, why is psi going from minus infinity to infinity?
Psi should go from minus epsilon Fermi to infinity.
But
I have to cover all my momentum space.
I thought we're just taking the thin layer around the epsilon, the Fermi surface.
You will see where the integral converges. The integral will converge very fast. I do not feel omega d pi. I do not need omega d pi. Actually, the integral will converge much before. You will see now.
Something which decreases the experiment.
So formally, I had to integrate.
So we don't have to do this manually. It will happen by itself.
You will see it. Yes. So now I want to have this integral non-zero. So this is xi plane. So where are the poles? First of all, this d psi over dp is V Fermi. Do you agree with me? This is velocity is derivative of energy over momentum. So this is V.
Why is there not Q anymore?
Sorry? No, one moment only. Epsilon is P squared over 2m. Psi was P squared minus P Fermi squared over 2m. D psi over dt is P over m. P close to P Fermi. So this is V Fermi.
But Q, what about?
No, Q I have. Q, sorry, I did mistake. Yes, of course. You're right. Oh, sorry. My mistake. VQ. So first pole is psi1 is E epsilon n minus V. Second pole CP is minus E epsilon n. So if both of them from one side, the integral will be 0. If they are here, the integral must be 0. So my integral will be proportional to theta function, which will manage me positions of poles. So epsilon n plus and minus epsilon n must be of the opposite signs. You agree with me? Look, this is the integral which I calculate by the Cauchy theorem. And I want the poles must be from different sides because I want to do this. So this theta function says me one pole is from one side, another from other. So it must be minus. They should be opposite. So this minus on this minus will give me plus. So I will put theta function epsilon n plus. Then I will close my contour in counterclockwise. So I will put 2pi. Claire, do I have still time?
Yes, I think you have 10 minutes.
10 minutes. Okay. So, and then it will give me, look, one. Let's suppose that omega nu is positive frequency. So epsilon, this will be epsilon n plus nu, and this will be epsilon minus epsilon n. E. So I take this pole and put here. So I will have, I take this pole, here n plus nu. So I will put in this pole here. So I will have minus p epsilon n minus xi of p, or minus xi. And then I will put minus xi. Minus xi will give me minus p epsilon n plus nu, and plus xi plus no, sorry, xi already is cancelled. So here minus minus and epsilon mu and minus p. So I took this value of xi in this pole, this one, and put here. Okay? How to calculate the Cauchy integral? You do not remember.
It always seems like magic, no matter how.
This is a theory of functional complex variable.
Yeah, I know.
Okay, I can derive you but
No, it's,
I don't have.
it's
Yeah,
fine.
you have a general formula in points analysis, like integral
Yes,
integral of poles equal to IP.
yeah, exactly. This I use namely this.
Then you count the windings around the pole.
So I say that the total integral here is 2 pi e sum of residuals.
Yeah, so this integral.
So I calculate this integral. I'm interested in. This will be 0. Why it will be 0? Because I have psi square in the denominator at large radius, and length will be only psi. So large radius in numerator divided square of large radius in denominator. So if I will tend it to infinity, it will go 0. So this piece is 0. So this is equal to 2 pi e for sum of all poles. The only pole is here. I calculated residual and I got you the answer that it is 2 pi theta function epsilon n plus nu divided minus 2 e epsilon n minus e omega nu minus v minus plus minus. So integration over momenta I perform. Now I have to calculate. I need to perform summation. T sum over epsilon n minus 2p e I will cancel, and here will appear plus vq. So I will have minus 2 pi, better
Minus.
minus 2 pi, theta function epsilon n plus nu, 2 epsilon n plus omega nu plus v. So in my polarization operator, I performed momentum integration. And
It's not the minus.
sorry, minus is here.
No, in the previous line, isn't it minus?
It was minus and I could cancel I.
Yeah, and at the denominator, isn't it?
In the denominator, I changed sign because it was just minus VQ and I divided
It was
I.
already minus.
So it is
Okay,
plus
E.
V.
Yeah, okay.
Now, how to do this summation? Epsilon n is 2 pi t n plus 1 over 2. This is fermionic superfrequency. So actually, my p is minus 2 pi sum from minus infinity to infinity theta function epsilon n plus nu 2 epsilon n plus omega nu plus e with. Okay. Look, 2 epsilon. Yeah, here I will put what is 2 epsilon n. So it will be 2 pt n plus half plus omega nu. Okay. And 2 pt out, and I will have p is minus. Temperature was here. Minus sum from minus infinity to infinity. Theta function epsilon n plus nu. N plus 1 over 2 plus omega nu 2 pt. No, not 4 pt. 4 pt plus, it was 2. So 2, maybe I lost some 2. Yes, 1 over 2. And here plus e v q divided 4. Very good. Theta function says that, look, let's suppose that I told you that omega nu is more than 0. So n 0. If n more than 0, so epsilon n positive, epsilon n plus nu even more positive. So all this interval for me is good. But look, if n is negative, but not very negative, so from here to minus mu, minus 1. So from minus, this is negative, this is still positive. So this interval is bad. Because here epsilon n is already negative, but epsilon n plus nu still positive. So I have to avoid it. And I have to write that my sum so my P will be equal to minus 1 over 2, minus 1 over 2, sum from minus infinity, minus mu minus 1, 1 over n plus 1 over 2 plus omega nu plus e equal for t plus sum from 0 to infinity 1 over n plus 1 over 2 plus omega nu for t plus e equal for t. You're still alive? You follow me or not?
Maybe you can explain again why you have to separate them.
I control that this theta function is 1, not 0. So arguments have the same sign.
Yes.
If n is positive, no problem.
Yes.
If n is negative, but very negative, no problem. But when n is an interval from minus 1 to nu minus nu, so this guy is negative and this is still positive. So I exclude this from summation. I wrote that my summation from minus infinity goes to the point minus nu minus 1.
Because you know the other part is 0.
Other part will be 0.
Yeah. Okay. Yeah.
Now I do the trick. I pass from summation from, what I will do, I will change n to minus n. So I will write summation from nu plus 1 to infinity minus n. I have right. Then I will shift my, what I will do, I will write minus, plus, minus, minus, minus. Okay? Now I will shift the variable from nu plus 1. Look, this is omega nu plus 1. Plus 1. I won't say that now I put minus here. And I want to return it. With infinity, you can do what you want. But I do not like this argument. So I will shift for nu plus 1 my n. And here I had, no, it is necessary to explain more precisely because I remember this. But so look, epsilon n is 2pt n plus half. So I will do the following. Look, minus sum mu plus 1 infinity. Claire, it is your fault because you told me that I do not have time. Okay. So 1 n minus 1 over 2 minus mu over 2 and minus mu. I will do the following. I will write that this is n prime, which, okay, I will do the following. N minus omega minus mu minus 1. And I will write plus 1 over 2 plus mu over 2. Do you agree? And minus 1 over 2 minus mu over 2. I write minus mu minus 1. Then I add half and I add half. Then I will say that minus sum from mu plus 1 infinity 1 over n minus mu minus 1 plus 1 over 2 plus omega nu for pt plus v. And I shift the variable. I will say that this is n prime 0 infinity. And I will see the first sum is like the second sum. And
With a frequency that is shifted.
sorry?
With omega that is shifted.
Yes, I shifted. Yes, but I have some problems with sign. So I did. Yes, because here I had to write signal of epsilon m plus u because I closed in this way. So because here must be plus. Okay, believe me, I do not have time. So because evidently that both sums should give me something the same. So finally, my p is sum from 0 to infinity minus 1 over 2. They give. Okay, let's put q0 for this moment for simplicity because I do not have time. I will show you how to calculate the sum and that's all. So sum 1 over n plus 1 over 2 plus omega nu for pt. Okay, I can write this sum from 0 to infinity 1 over n plus 1 plus omega nu for pt minus evq and here plus. Does not matter. This sum is calculated in terms of polygamma function. So it is an Euler, the derivative of Euler gamma function. So it is psi of infinity. So the derivative of Euler gamma function at infinity, which is logarithm, large logarithm, minus psi function of 1 over 2 plus omega nu for pt minus plus evq for pt minus psi of infinity. So what I say? Something I do, something. No. It's okay. Okay. And yes, this is okay. And minus psi function, the same psi function, but with minus e. Exactly. So plus. So we have divergency. Psi function of infinity is bad. But here I have to include physics. So you saw that I did not have any problem with integration of psi. So it does not matter infinity, that the fact that I extended to infinity, we did not feel, because all happened at the scale of temperature, which is much less than omega d pi. So we did not arrive to omega d pi. So the integral was well convergent. Now, unfortunately, I come to the problem, because summation of 1 over n is divergent. And I have double such sum, so it is finally 2 psi of infinity minus psi function 1 over 2 plus omega nu 4pt plus EV for pt minus plus minus psi function 1 over 2 plus omega nu for pt minus EV for pt. Great. Here it is necessary to remember what I'm doing. I'm summing over the Matsubara fermionic frequencies. This is energy, and energy cannot exceed the omega d pi, because all happens in this skin of orange. So maximum n, which I can admit here, would be epsilon n of the order of omega d pi divided to pt, because this is not epsilon but n. So n maximum is omega d pi divided to pt. I'm finished. Sorry, I'm finished. So I have find that p is p is what I lost. No, I did not lost anything. Will be g g must be here probably. Okay, we will try. Logarithm omega d pi 2 pt minus psi function 1 over 2 plus omega nu 2 pt and then plus EV 2 pt and minus psi 1 over 2 plus omega nu 4 pt inside EV2 4 pt. And if we have to average this over directions, I forgot about integral over q, because this is v q, here is cosine, so finally I will have q square. Okay, let's leave it in this way. So now L minus 1 is J minus 1, J minus 1 minus P. So what I will have, the J, no. Sorry?
Then you probably don't have the G in front of it.
Yes, I should not have G. Yes. So I put it by hands. Yes, exactly. So, very good. TC is gamma E divided P omega d pi exponent minus 1 over G. This is a BCS form. So I can get it. I can say that I'm in normal state. There is interaction of electrons in these Cooper pairs. They appear, disappear. But at the point of superconducting transition, I have reconstruction of the ground state. So these two particle green functions should have a pole. If it has pole, so L minus 1 should be 0.
At 0 frequency.
At 0 frequency, at 0 momentum. Exactly. So I took this guy and put here. And so it will be minus 2 C function of 1 over 2. And I will have this equality. So this must be 1 over G. It's okay? Yes, it must be. So this will be coefficient, this gamma Euler, etc. So I see, and this must be TC, because here happened TC. So I will get that TC is, I will put an exponent minus, and I will get you the BCS formula. So if my Cooper pair, which was formed with zero frequency and with zero momentum, it will give me the BCS critical temperature pole. But I have more. I did all this suffering to get you something more. So I will return that L minus 1 is 1 over G. And now I want that 1 over G is log omega d bar divided 2 PTC. And then minus pi, which will give me this logarithm, but a temperature. So finally, I will get that L minus 1 of Q omega nu is minus 1 divided density of states, 1 over log T over TC plus psi function 1 over 2 plus omega nu 4 pt plus T square 4 pt minus psi 1 over 2. I did not have time to be more detailed, but so, and this is the two particle function, which allow, and we will tomorrow call this line, and then we will understand how we can calculate any thermodynamic and kinetic the transport properties, having enhanced this propagator. Okay, thank you. Sorry for I was not too precise.
Thank you.
Sorry, I did not do this. This exercise maybe 25 years, so I made some mistakes. I don't remember everything.
Okay. After 45 years, I'm not sure I would be as short.
Yeah.
Any further question?
Yeah, please, questions. Yeah.
Maybe just a slight remark on the question on the notation. So in the very last formula,
Yes.
in the denominator, in the sum, in the exactly in the d gamma function.
Yes, this is the gamma function.
Yes, and then the sum.
Then 1 over
yes.
omega nu divided 4 pt.
And then the last.
And this is dq square over 4 pt. And dq square,
yes.
Because you see we had, this is properties of, because I have plus EVQ and minus EVQ. And I have to, but VQ is a scalar product with cosine. This is scalar product. So when you integrate over the angles, you will have this cancellation. And finally, you so imaginary parts will each okay, psi function is an analytical function. So this has evidence that they have the same, not here, the same imaginary parts, but of opposite sign. When I sum them, they cancel out. So the next order will be Q square. I don't know if I explained myself or not.
But what is D?
D is an electron diffusion coefficient.
Yeah, so now the elastic mean free path has entered into the
Exactly.
back door.
Yes,
Didn't
exactly.
enter
This will be
earlier.
psi. Actually, finally, it will be psi square because you have D electric divided temperature. D Q square divided temperature. And you remember that psi is the square root of a dirty superconductor is the square root of d t. So from this, I will. This is general because we got this very rich formula close to Tc when this small and omega I do analytical continuation minus e omega. So I can for omega less than temperature and small momenta, I will expand this, and I will get L of Q, L without minus 1. It minus 1 over nu, 1 over logarithm close to TC, T close to TC. So it will be almost 1. So I will write T minus TC over TC minus P omega over 8 TC plus psi square Coulomb square. This will be the propagator close to TC. And you see that this is a fundamental solution of time-dependent Ginsburg-Landau equation. So here you see that close to TC, all this machinery is not necessary. It would be possible to write time-dependent Ginsburg-Landau equation, solve to find its fundamental solution. So I wanted to show you the beauty that London equations follow from Ginsburg-Landau. Ginsburg-Landau follows from microscopic theory. It was a famous paper of Garkov who enriched Ginsburg-Landau by the values of microscopic 2 coefficients of 3. And third one, as Mohit told today, and I told that the third one, no, depends on normalization, what we will identify as same function. Okay, thank you for your questions.
So you could understand that what